Eric Rowland from Hofstra University, and he is going to speak today about avoiding fractional powers on an infinite alphabet.
Thanks very much for the invitation. So we're going to begin with the founder of our field, Axel Tuohy, who I guess over 100 years ago now was asking questions like this. So a square is a non-empty word of the form XX. And he was interested in questions like, can you build arbitrarily long words, say over the alphabet 0, 1, that don't contain any squares? And I guess everyone here probably knows this this exercise, but if not, you can just try to construct one. Say we'll put down a 0 if we can, if it doesn't introduce a square. So we can start with a 0, and we can't put down another 0 because that would introduce the square 0, 0. But we can put down a 1, and then we can put down a 0 after that because that doesn't introduce a square. We can't put down a 1 there because that would have introduced the square 1, 1. But now we're stuck. We can't put down a 0 because 0, 0 would be a square. And we can't put down a 1 because 0, 1, 0, 1 is also a square. And so you can check that this is the longest square-free word that you can possibly build, length 3, on a binary alphabet. So in this talk, I want to give ourselves a lot more freedom and just work over an infinite alphabet. So we'll never run into this problem that we don't have another letter to put down when we're building one of these words that avoids a pattern. So what I'm going to be interested in is the lexicographically least square-free word or word avoiding some other pattern on the alphabet of the non-negative integers. So why am I interested in the lexicographically least? Well, most patterns or most languages, if you're trying to avoid them on an infinite alphabet, it's very easy. Like I said, you always have a letter that you haven't used yet, so you can always put that letter down. Unless your pattern is very special in some sense, then you'll be able to avoid that pattern. So one possibly interesting question is, what is the lexicographically least such word? And so where we got stuck before, 0, 1, 0 on a binary alphabet, now we can put down a 2 because since we haven't used that letter yet, there's no chance that it'll introduce a square. And this will let us keep going. So the next letter we could put down is a 0. And then we can't put a 0, but we can put a 1. You can put a 0 next. And now you can't put a 0 because 0, 0 will be a square. You can't put a 1 because 0, 1, 0, 1 will be a square. And you also can't put a 2 because 0, 1, 0, 2, 0, 1, 0, 2 is a square, but you can put a 3 and go on from there. So this is a sequence you may recognize. It's called the ruler sequence. And this characterization of the ruler sequence appeared in a paper by Mathieu Guépaquet and Jeff Shalit from about 10 years ago. And they proved this theorem that this word is generated by a morphism. So this is a morphism that takes each letter n. So this is going to be a non-negative integer and replaces it with 0, n plus 1. And if you iterate that morphism, here are the first few words you get, right? Phi of 0 is 0, 1. Then when you apply phi to that, the 0 becomes 0, 1, and the 1 becomes 0, 2. And then on the next step, you'll get a 3, etc. In the limit, you'll get a fixed point of this morphism, and that is this lexicographically least square-free word on the non-negative integers. And this morphism is 2 uniform, meaning that the image of every letter has length 2, right? So 0, n plus 1 is a word of length 2. And that's not a coincidence. It's that 2 is related to the fact that we're avoiding squares here. So their more general result is that if you take any positive integer a greater than or equal to 2, and you define this morphism phi of n to be not 0 followed by n plus 1, but a minus 1 zeros followed by n plus 1, then the lexicographically least a power-free word on the non-negative integers is the fixed point of this morphism. And so this is an a uniform morphism. All right, so for squares and cubes and fourth powers, we know what the lex least word avoiding that pattern looks like on the non-negative integers. In that same paper, they also looked at overlaps. So again, probably everybody knows this, but an overlap is a word of the form XXC, where C is the first letter of X. For example, 0, 0, 0 is an overlap, 0, 1, 0, 1, 0 is an overlap. And 2A was also interested in overlaps. So he showed that even though squares are not avoidable on a binary alphabet, overlaps are avoidable on a binary alphabet. And in particular, you can construct arbitrarily long overlap-free words using the 2A morphism. So this is on a binary alphabet. This will give you not the lex least, but close to the lex least overlap-free word on a binary alphabet. Here are the first few images, iterates under 0. So what about an infinite alphabet? Well, here is a prefix of the lex least overlap-free word on an infinite alphabet. And what Mathieu and Jeff realize is that the way to look at this word is to look at it like this. This is, if you break it up into blocks like this will really show the structure. What we want to do now is let this first block be phi of 0, and this is going to be another phi of 0, and this is phi of 1, and this big block over here at the end is phi of 2. And if you define phi of 0, phi of 1, phi of 2 like that, then it looks like this word is a fixed point of this morphism, right? So in the bottom row, we have phi of 0, 0, 1, 0, 0, 1, which is exactly what the word is itself. So what is this morphism in general? We'll need the right shift map. So this is just going to be a function that takes finite words and moves the last letter, the rightmost letter, to the beginning. So sigma of xc is going to be cx, for words x and letters sigma. And what they showed in that same paper is that if you define phi recursively, so phi of n is going to be n iterations, n applications of phi to the word 0, 0. Then you shift that word by 1 and append n plus 1 at the end. If you define phi recursively like that, then phi infinity of 0, this fixed point is going to give you the lex least overlap-free word on the non-negative integers. So let's just check what this definition says. So when n equals 0, we should get 0, 0, 1, right? So when n equals 0, we're applying phi 0 times to the word 0, 0. So we get the word 0, 0. When we rotate right, that's still the word 0, 0, and then we append the letter 1. So we do, in fact, get 0, 0, 1. Phi of 1 says we're going to apply phi once to the word 0, 0. So we'll get 0, 0, 1, 0, 0, 1. We'll rotate that word once. So we'll take the rightmost 1 and put it on the beginning. So we'll get 1, 0, 0, 1, 0, 0, and then we'll append a 2. And that's exactly what the image of 1 is. So this is a non-uniform morphism, right? So so the phi of 0 has length 3, phi of 1 has length 7, and the lengths grow according to some recursive sequence. Yeah, and so here are the first few iterates. So we have squares and cubes and fourth powers. We also have overlaps. In this talk, I'm going to focus on fractional powers. So here are some examples of fractional powers. 1, 2, 2, 0, 1, 2, 2, 0 is a 5/4 power because it consists of the word 0, 1, 2, 2 followed by its first fourth. So that's the 1 plus a fourth, that's the 5/4. 0, 1, 1, 1, 0, 1 is a 3/2 power because it consists of the word 0, 1, 1, 1 followed by its first half. So here's the definition. We're going to want a over b to be greater than 1. And the idea is that fractional powers are sort of partial repetitions. They're not, a 3/2 power is sort of halfway between a first power and a square. So here's the definition. A word is an a over b power if w equals xy raised to some positive integer e followed by x, where x and y are any words. And we want the ratio of the lengths of y to its sort of base, xy, to be a over b. So for example, 5/4 powers look like xyx, where y is 3 times the length of x, right? Because then the ratio of the length of y, length of w. So what is the length of w? The length of w is 5 times the length of x. And the length of xy is 4 times the length of x, so the ratio is 5/4. And similarly, 3/2 powers look like xyx, where y and x have the same length. And these two fractions, 5/4 and 3/2 in particular, are going to be sort of central in the talk, so that's why I'm giving you examples of those. I should say, feel free to interrupt me with any questions at any time if there are questions. This is the main object of the talk. So let w sub a over b be the lexicographically least a over b power-free word on the non-negative integers. And we're going to assume that a and b are relatively prime for the obvious reason that if they're not, you can just cancel their common factor. Okay, so let's look at some examples. So what about 3/2 powers? What is the lex least word avoiding 3/2 powers? So we can play the same game when we try to build it one letter at a time. We start with 0. We can put a 0 down next, right? This is a square, which is greater than a 3/2 power numerically, right? But it's not a 3/2 power because we're only avoiding exact 3/2 powers. So the 0 here is perfectly fine. We can't put a 0 down next because 0, 0, 0 is a 3/2 power. So we have to put a 1. We can't put a 0 next because 0, 1, 0 is a 3/2 power, but 1 is okay. 0 is okay next. Can we put a 0 down next? No, we can't put a 0 down next because 0, 0, 1, 1, 0, 0 is a 3/2 power. We also can't put a 1 because 1, 0, 1 is a 3/2 power. So we have to put a 2. And it goes on from there. So what is the structure of this word? Well, it's a little easier to see when we break it up into blocks of length 6, it turns out. And so now you can see that, that the columns here seem to be periodic. And this last column, except for the last column, which contains all the numbers that are larger than 1. Here's another way of looking at it, which is a graphical form. So here what I've done is I've taken the same word and broken it up into blocks of length 6. But now I'm coloring each 0 letter as a white cell and each 1 letter as a light gray cell and a 2 as a slightly darker gray and so on. So it's just a little easier to see the structure here. And when we go to look at more complicated words, I'm going to use this type of picture to show you what the structure looks like more easily. Okay, so that answers some things. So the first 5 columns seem to be periodic. What about this last column? So this last column is 2, 2, 3, 3, 2, 4. And in fact, that has a relationship to the sequence itself, 0, 0, 1, 1, 0, 2. Turns out that this last column is a copy of the word, but where every letter is just shifted up by 2. So this appeared in a paper that I wrote with Jeff in 2012. The ith letter of this word w3/2 satisfies this recurrence. So the first 5 columns are periodic, and then in the 6th column, I should say, we're starting indexing all words from 0. So this last column is really the first column is the 0th column, and the last column is the 5th column. So the letters in this last column here are at the 6i plus 5 positions, and they exactly correspond to the word in the letter in the ith position, just shifted up by 2. And from this recurrence, you can easily write down a morphism that generates that generates this word, and we'll do that later on in the talk. At this point, I want to talk about some other notions of avoidance. So in combinatorics on words, it's not as typical to just look at the notion of avoidance that we're using here, where we're just interested in avoiding A over B powers. It's been more common to be interested in avoiding, say, A over B and all powers greater than A over B at the same time. And so we can certainly look at those, right? So we could define 2 additional words for every rational number A over B. W greater than or equal to A over B is the Lexley's word avoiding P over Q powers for all P over Q bigger than A over B. And the strictly greater than version is just avoiding all P over Q powers strictly greater than A over B. And I think it's an interesting question. What are the relationships between these 3 words? If there are relationships. In a couple cases, there are relationships. And actually, we've already seen one of these words, right? So the Lex-Least overlap free word on the non-negative integers is W strictly greater than 2. And we said that that was generated by a non-uniform morphism. So in some sense, at least the first one, W A over B, seems to be a lot simpler. In the morphism is much easier to write down. It's a uniform morphism than W greater than 2. So my hunch is that the first of these words, the ones that we're looking at in this talk, are the simplest. But there hasn't been a whole lot of work done on these other 2. But I will mention a couple relationships between W A over B and W greater than or equal to A over B. So if we avoid greater than or equal to 3/2 powers, the word looks like this. And instead of breaking things into blocks of length 6, the right number here is length 5. So again, the first few columns are periodic. This last column is where all of the higher letters appear. But instead of having a relationship to this word itself, right? So here we're getting 3, 3, 4, 4, 3, 5. That doesn't look very much like 0, 1, 2, 0, 3. Instead, what it looks like is the other 3/2 word, the W 3/2. And so the structure of this word is really reflecting the structure of the other word, or vice versa. They have the same underlying structure. They just differ by a morphism or something like that. But arithmetically, in terms of the recurrence, it seems to be easier to write this word in terms of the W 3/2 word rather than the other way around, because the W 3/2 word sort of is self-similar. It has the self-similarity of itself built in, whereas W greater than or equal to 3/2 sort of, to me, it's sort of looking back at the W 3/2 word. To write a morphism down for this one, it's a little more complicated. So we have this relationship for W greater than or equal to 3/2 and W 3/2. 4/3, there's also a relationship. This is a conjecture, I should say. On the top here, we have W greater than or equal to 4/3. If you can, I don't know if you can tell, but there's one column right here that is not periodic. This is broken up into 336 columns. This is W 4/3 broken up into 56 columns. It also has one column that is not periodic, not eventually periodic, I should say. And there just seems to be less going on in this picture than in the top picture. But if you look at the 2 columns, the one in this picture and the one up here that are not eventually periodic, you can actually see the same structure there. It's hard to see, but if you get real close to your screen, there's 3 dark cells followed by sort of an alternating pattern, and then 3 more, and that's what we're seeing right here: 3 dark cells and then some alternating, and then 3 more. So these are basically the same sequences. So here's the recurrence, or the formal relationship between these 2. Between just those 2 columns, and this is a conjecture. We do know what the structure of W 4/3 is. That is a theorem. but the structure of this upper word is just a conjecture. So that's why this is also a conjecture, the relationship between these two words. So, so for 3/2 and for 4/3, we have this relationship. I don't know if there are other rational numbers where these two words are related. Probably there are, but honestly I haven't looked at it too much. So if anyone is interested in looking at this, I would definitely encourage you to do that, because there could be some interesting things out there. But for this portion, for this reason, this is why I'm going to focus on WAB in the talk. It seems to be the simplest of the three. And there's already plenty of complicated things going on for that word itself. So let's talk about large rationals, which for purposes of this talk means greater than or equal to 2. So W5/2, this is the Lex Least word avoiding 5/2 powers. This looks like this, 0, 0, 0, 1, 0, 0, 0, 1, etc. It looks like we should be able to write down a morphism for this word fairly easily. It turns out this is exactly the same as W5, which was covered in, right? So this is the word that avoids 5th powers. So this was covered in Mathieu and Jeff's paper. It's generated by this morphism. And this is a general fact that if you have a rational number greater than or equal to 2, then it's a word we've already seen. WAB is just WA. Here's a proof of one direction. The other direction is slightly more complicated, but not too much more complicated. So if we take an A power, V to the A, that's also an A over B power, because we can write it as V to the B to the A over B. WA over B is the Lex Least A over B power free word, right? But if every A power is an A over B power, then WAB is also A power free. But WA is the Lex Least A power free word. So that must mean that WA is lexicographically less than or equal to WA over B. And using a similar but slightly more complicated argument, you can show that WAB is lexicographically less than or equal to WA, and so they must be the same word. So this really cuts down the, well, in some sense, not in a cardinality sense, of course, but in an intuitive sense, it cuts down the number of rationals that you have to look at if you want to understand what's going on for all rationals. It suffices to look at the interval 1 to 2. And there's still plenty of interesting things that happen there. So when you're looking at these, all of these results so far, they were discovered experimentally, right? So you have to, you take one of these words, you compute a long prefix, and then you have to try to figure out what is the right size to break the word into, right? Into the right block size. So here is W8/5 partitioned into blocks of size 100, and you can see some structure there, but it's nothing that's going to let you write down a morphism immediately. So there's a lot of experimenting that goes into finding the structure for these. It turns out that 733 is the right number. So if you can see, again, this is really small, but the very last column over here, that's where the interesting stuff is happening. All of these other 732 columns seem to be periodic. And in fact, this word is generated by a 733 uniform morphism that, which is complicated. But on the other hand, it's a word on 0 and 1. I guess here's a 2 here. 0, 1, and 2 of length 732, followed by an n+2. So yes, it's complicated in the sense that you have to, specify 732 pieces of information or something like that. But in some sense, it's simple in the sense that it's a word followed by the morphism phi of n replaces n with some constant word followed by n+2. Here's another one. This is a particularly complicated one. This is W7/4. Here's a picture where I've broken W7/4 into blocks of size 50,847, and then that would be really long, so that I'm line breaking the blocks. to get it all on one page. And again, this is, it's some fairly long morphism, but it's fairly simple in the sense that it's just replacing n by some long word followed by n+2. And I'll talk about how these things are proved in a little bit. But just here's a couple more. This one is a little bit more interesting because there's this messy transient region at the top of the picture. So the columns take quite a while to settle down into their eventual state. Let's see if we can find, yeah, so right here, I think this is the non-periodic column towards the right end of this picture. This is 1001 columns. So there's a transient region here. You can get this, you can capture this transient using a morphism by introducing a new letter 0 prime, and then defining the morphism as it is down here, where if you're applying the morphism to 0 prime, then you have this V word that basically captures everything that goes in this transient, and then kicks off the morphism, kicks off the word with phi of 0. And then you also need a coding. So you need a coding to then take this 0 prime and replace it with 0. And then the coding leaves all the other letters the same. Here's another one that's really interesting because this word turns out to be a word on a finite alphabet. So this is W7, 27 over 23. And you can see here, this is the self-similar column where the sequence repeats. But where it repeats, it's not shifted by anything. So I've highlighted this 0 here. On the previous morphisms, let me skip back a slide. On the previous morphisms, right, we had an n+2 here. Here we had an n+2. Here was an n+2, right? So whatever this shift up is, that's gonna increase the alphabet, right? If you're applying the morphism to 0 and it shifts it up by 2, then you suddenly have a 2, or maybe you didn't have any 2s before. And so as long as this number is non-zero, the word is going to actually be a word on an infinite alphabet. And of course, that's how we're defining it, so it's not that surprising. What is surprising is when this number is 0, then whatever letters you start with in your sort of initial transient portion and whatever letters appear in U, that's it. You're not going to generate any new letters by applying the morphism. So in fact, this is a word on a 3-letter alphabet, which means that the lex least word on the non-negative integers that avoids 27/23 powers is the same as the lex least word that avoids those powers on the alphabet 0, 1, and 2. And this was a bit of a surprise. This doesn't happen very often, but it happens for a few rational numbers. All right, here's another interesting one. This one, W5/3, this has a much simpler structure than the ones we were just looking at. Turns out if you break it into blocks of length 7, you can write down a morphism fairly quickly. Here's a recurrence. Again, this last column is just the sequence shifted up by 1 in this case. So here this number is 1. And this morphism is very similar to the morphisms that generate the A power free words for integers A. Instead of having a bunch of zeros followed by n+1, we have a bunch of zeros with an extra 1 thrown in somewhere, followed by n+1. And the reason that this one is interesting is because it actually is part of an entire family. Here's an entire family related to W5/3. They all have essentially the same structure, just in a slightly different scale. So this is a theorem that Laura Pledwell and I proved. If you have a rational number A over B between 5/3 and 2, where A and B are relatively prime and B is odd, then the lex least A over B power free word is a fixed point of this 2A minus B uniform morphism. So again, it's just a bunch of zeros, a 1, and then some more zeros, followed by an n+1. And we found several infinite families like this. So there are some theorems here. It's not just these isolate, it's not like everywhere you point your camera, you get a completely different behavior. It's a mix. So we have some infinite families. The smallest rational, after this paper with Lara, the smallest rational number whose structure of the word WA over B we didn't know was 5/4. So that's what I want to focus on for the rest of the talk, is the W 5/4. It wasn't for lack of trying. We looked at this in a lot of different ways. If you wrap it into 72 columns, you get this picture, which shows that there is some structure here, right? Several of the columns have become constant at this point. Several of them have not. Here's that same picture, but just continued for a lot more rows. This is the first 2,000 rows, and it really takes this long to see what's going on with this word. In this last panel over here, you can finally see some of the other columns enter their eventually periodic or eventually constant state. So this column becomes constant right here. This column becomes constant right here. This column over here, still all the way over here, still hasn't reached its final period until about here. So once it becomes here, then it becomes periodic. And then at this point, sort of in this last half of the last pane here, we only have one column left that is not periodic. And so this is necessary, but not sufficient, because then, you know, once you've isolated this column, then you have to somehow relate it back to the whole sequence to get the recurrence, which will lead you to the morphism, which will tell you what the structure of the word is. So what we did was we took that column, and this is work with Manos Pilati. We took that one column that had not become periodic yet. This is the 31st column of the 72, and we plotted it. Here's just a plot of the actual values of the letters that appear in that subsequence of W 5/4. And this was just one of the many things we were trying, because, you know, you try everything when you don't know what's going to work. And this is a plot of the sequence itself. And we noticed there is a relationship among these two plots. Specifically, if you look at the peaks. So these peaks right here, these are 6s in the word, W 5/4. These peaks are 8s in that particular column. But these 6 peaks certainly look like they have the same relative spacing as these 6 peaks. And then if you go over here, you have this collection of peaks that looks like this collection of peaks. And so if you line everything up, you can get a conjectural recurrence. And so this is the conjectural recurrence. And it turns out that 72 isn't the most natural size to block this word up into. It's actually 6, box of size 6. So here we're picking up the fact that there's a shift by 2. So here these letters 6 in the word get reflected as 8s in this self-similar column. But if you look at instead of looking at 72 columns, if you look at 6 columns, you can also match up the column that contains this sequence with the original word. It's just that the shifts are different. So sometimes you have to shift up by 1, sometimes you have to shift up by 2, by 3, depending on where you are mod 8. So this says that if you go very far out in the word, after 123,000 letters, then every 6th letter is related to earlier letters starting at the 5,920th letter, plus some shift. So this number, this 123,061, this is a type of, this sort of is the transient that says, well, things, you know, the word takes a while to settle down. So in other words that we had studied, we had seen transients like this. It just says, well, you have to go pretty far out until the structure of the word becomes clear. This number, this 5,920, this is not something we had seen before. What this is saying is that when you look far out in the word, those letters are related to letters earlier in the word. But what this 5,920 means is that they don't look back to the beginning of the word. It only looks back to letters starting at 5,920. So this was something new, and this is one of the things that made this word a lot more complicated and a lot harder to guess the structure of than other words we had looked at before. I'll tell you what the morphism is, but first I want to go back to W3 halves because the morphism is analogous in some ways. So we already looked at this word. We said if we break it up into blocks of length 6, then we get some nice structure. Since we have this periodic business going on with the first 5 columns, the idea is to use 2 different kinds of letters in our alphabet. So we'll take our alphabet to be sigma 2, where the letters are integers with a subscript that's either 0 or 1. And then the coding at the end, we'll just forget the subscript. So the 0 or 1 will keep track of which row we're on, essentially, because we should either put down a background 0, 0, 1, 1, 0 if we're on certain rows, but if we're on the other rows, we should put down a background of 1, 0, 0, 1, 1. So if we're seeing an N0, then we should replace N0 with this word, and if we're seeing N1, we should replace it with this word. So this is a 6 uniform morphism, but it's letting us keep track of which row we're on. And so these subscripts increase by 1 modulo 2, 0, 1, 0, 1, 0, 1 across each image, all right, because that way we're going to keep track of the row. And if you start with 0, 0 and apply this morphism, then you're going to approach a fixed point. And then if you apply the coding, then you get W3 halves. Okay. The morphism for the 5/4 power word is similar, except we need more letters. So the background here's a portion of the word. This is not at the beginning because the beginning has all sorts of weird stuff going on. But after you get into the portion where it's where the 5 of the 6 rows have stabilized, this is the kind of picture you see. And here the columns, the first 5 columns are periodic with period length 4. But we need 8 letters, not just 4, because the sequence of differences depends on where you are modulo 8, like we saw. So this sequence here, by the amount we have to shift up the letter by, is 3, 2, 3, 2, 1, 2, 1, 2. So that repeats every 8. So we have to keep track of that as well, not just the background. But other than that, then this morphism is just determined by what the background has to be. So these first 5 columns are just encoding this background. And again, the subscripts increase by 1, but now they increase by 1 modulo 8 because we have 8 different copies of each letter. And another feature here is that when we get to the end of an image, right, this is a 6 uniform morphism, but we have 8 letters. So we don't complete a period of length 6, of length 8 rather, in the 6 uniform morphism. So when we have a subscript 5 in this, at the end of this image, then the subscript at the beginning of the next image has to be 6, and so on. So the sigma 8 is the alphabet that contains 8 copies of each letter, 1 for each type of row that we're on. And our theorem is that there exist words P and Z of lengths 6,000 and 20,000, such that W5/4 is of this form. So this also does not look like the other results. The other results were very clean fixed points of morphisms. Here, this looks like a fixed point of a morphism, but it's missing a Z out front. And then we have to prepend this, we have to add this period to the beginning, this prefix to the beginning. So it's much messier. What are these words? The word P is a word on the non-negative integers because it's actually a prefix of W5/4. The word Z is a word on this alphabet sigma 8. So it is a word that has integers with subscripts assigned to it in an increasing way. But a peculiar fact is that this Z actually contains some negative 1s. So it contains -1 sub 0 and -1 sub 2. Even though this W5/4 is a word on the non-negative integers, to describe it like this, you need to put some negative integers, well, just these two types of integers, negative integers in Z. And then what happens is, since all of the occurrences of Z actually get actually appear inside phi, right? We're applying phi to every occurrence of Z here. So these negative ones are going to end up being 0 or positive after we apply the morphism at least once. All right. So the proof is quite technical. Here's just the basic outline for all of these words, not just for the 5/4 power free word. What you want to do is you show that the word you think is WA over B avoids A over B powers, and then you also have to show that it's Lex least. So that means that decreasing any letter in the word will introduce an A over B power ending at that position, so that each letter is as small as it possibly can be. But here was another surprise, and I mentioned this in the abstract. For all of the previous studied words, step 1, showing that the word that you think is your word, showing that that word is A over B power free, involves showing the morphism that you have is A over B power free, meaning that the morphism preserves the property of being A over B power free. So if you have a word W that is A over B power free, and you apply the morphism to it, then you get a new word that is A over B power free. And that just fails completely for this morphism for the W5/4 power free word. For any integers n and m, we could take this very small word, 0 sub 4, m sub 5, m sub 6. This word is 5/4 power free just because it's too small to contain any 5/4 powers, but its image does contain a 5/4 power. So its image is this. I know you don't remember the morphism, but you can sort of figure out what it's doing. So 0, 4, the subscript 4 means the background is going to be these first 5 letters, and then it's going to increase the 0 to a 1. So the last letter is going to be 1 sub 5. The image of n sub 5 is this, and the image of m sub 6 is this. And so since we have this 1, 4, 1, 5 in both places, this is a 5/4 power of length 10. So this morphism does not preserve 5/4 power freeness. So we had to create a workaround to this. Our workaround was to consider a notion of pre-5/4 power freeness. So we call a word a pre-5/4 power under this morphism if it becomes a 5/4 power when you apply phi. So for example, this word is not a 5/4 power because 0, 0, and 2, 4 are different letters. But if you apply phi to it, you do get a 5/4 power. So it is a pre-5/4 power. And again, what is the morphism doing? It's sending the 0, 0 to this word, and it's increasing the 0 by 3 in that last letter. And to 2, 4, it's going to increase that 2 by 1. And so what you end up getting is the 3, 5, 3 sub 5 in both places. And the backgrounds agree. These first 5 letters, 0, 0 through 1, 4, these are the same because these subscripts are differ by 4. Okay. So every 5/4 power is a pre-5/4 power because, of course, if you have a 5/4 power and you apply phi to it, you're going to get another 5/4 power. But there are pre-5/4 powers that are not 5/4 powers. And so the idea was, well, if phi doesn't preserve 5/4 power freeness, maybe it preserves pre-5/4 power freeness. And it turns out that it does if you're careful. So we have to let gamma be the set of this particular set of letters. Most of these letters aren't going to be of much concern because most of them are negative, but we do have to worry about some of them. There are a couple zeros in here. And like I said, there are some negative ones in our word Z. So we also have to be careful about that. But if you have a word that doesn't contain any of these bad letters, then this proposition says if you have a a pre-5/4 power free subscript increasing word. So that means that the subscripts increase by 1 modulo 8 from one letter to the next. And it doesn't contain any of these letters, then phi of w is pre-5/4 power free. And we can apply this to z because z is a subscript increasing word that doesn't contain any of these letters. So here's the long sequence of results that was necessary to establish that the conjectured word is actually 5/4 power free. We showed that this word z followed by phi of z, phi squared of z is pre-5/4 power free. Since that word is pre-5/4 power free, then by the previous proposition, when we apply phi to it, we get another pre-5/4 power free word. So that step is easy. This theorem is not easy, but the corollary is easy. Since now this word is pre-5/4 power free, and every 5/4 power is a pre-5/4 power, that means that this word also is 5/4 power free. So that's easy. But then there are two remaining steps, which are that once you apply the coding, you have to, right, the coding forgets the subscript. So you have to show that you don't introduce any 5/4 powers once you apply the coding. And then you have to tack on this prefix at the beginning of the word and show that that still doesn't introduce any 5/4 powers. So this was quite complicated for this word. Lexicographic leastness this is the other step. This was a little simpler. All I'll say about this is that it's a case analysis and sort of a complicated induction. But both of these steps required large checks to be carried out by computers. So there's a lot of case analysis in both these cases. I'll just finish by talking about regularity a little bit. So maybe many of you know this already, but a sequence is k-regular if all of the subsequences of this form are contained in some finite dimensional Q vector space of sequences. So for example, if we go back to the word W2, this was the Lex least square free word over the non-negative integers, and we let Wi be the ith letter, then this was generated by a morphism that sends n to 0, n plus 1, right? So every even indexed letter is 0. And every odd index letter, W2i plus 1, is simply Wi plus 1, because that's exactly what the morphism does. So these two recurrences or equations, if we look at other subsequences of this form, so this is W a power of k times I plus a remainder mod k to the e. If we look at higher powers of 2, so 4i plus 0, 4i plus 1, etc., we can use these two recurrences and sort of by reading I in base 2, or reading this number in base 2, resolve this down into linear combinations of sequence Wi and the constant 1 sequence. So these two sequences, Wi itself and the constant 1 sequence, generated a two-dimensional vector space in this case that contains all of these subsequences. And since that vector space is finite dimensional, this sequence is 2 regular. So 2 is the k here. So it turns out that many of these sequences, all of them we've been able to understand the structure of, they're all k regular for some k. This was to prove that the 5/4 power free word is k regular is for some k. So here the k will be 6. You can do it from the recurrence using this theorem. So here's a relatively complicated recurrence, but what this is basically saying is this is of the form that we've been looking at. So you have some sequence Wi, and every k terms looks back at this earlier terms in the sequence, shifted up by some amount d of I, which is a periodic sequence. And then the terms in between, they are given by some periodic sequence u. Yeah, anyway, this is a fairly technical theorem, but what it lets us conclude is it lets us put an upper bound on the dimension of the vector space containing all space 6 shifts of W5/4. And from that, we were able to actually establish the dimension of the vector space, the minimal dimension of the vector space, to be 188. So we say that the sequence of letters in W5/4 is a 6 regular sequence with rank 188. And just to show you how that compares with other sequences, here's a table of the first few rational numbers sorted by their denominator. These are rational numbers between 1 and 2. And the k is the value of k for which the sequence WA/B is k regular. So we saw several of these sequences earlier on in the talk. Some of them are very complicated, right? The 7/4 has k equals 50,847. 5/4 has a very small value of k. It's just 6 regular. But the interesting thing is that the rank is very high. So it's the highest rank that we have of a sequence of this form WA/B. And the reason goes back to this number 5,920. It's the first word where the S in this recurrence is non-zero. So in other words, the recurrence doesn't look back to the beginning of the word, it looks back to some portion of the word after, well after the word has started. So this is just this table kind of looks like a mess. It's very hard to see any patterns in here. There are some, we did talk about some theorems. So the word 5/3 belongs to an infinite family with 9/5, in other words. So this isn't, there are other ways to look at the data that will make it so that you can see theorems a little bit more easily. But there are a lot of these words that are just, as far as we can tell, don't belong to any families, and they're just sort of one-offs, and you have to prove them on their own. There are also words that we just don't know the structure of. So this bottom row, 11/6, we don't even have a conjecture for the structure of the 11/6 power free word. So a big question is every word k regular for some k? And it's seeming increasingly likely, because for most of the words that we've really tried hard, we've been able to find their structure, and the sequence of letters is k regular, but they keep getting more and more complicated, and so we don't really know what the end game is going to look like. And without having some bounds for these numbers, it's hard to imagine proving a theorem like this. Let me just end by putting up the two morphisms for 3/2 and 5/4 on the same page. So these are both 6 uniform morphisms. So both of these words are 6 regular sequences. I don't know if that's a coincidence or if there's something there. In some sense, maybe it's the morphisms that are more natural than the Lex-Least words. Right, the Lex-Least words are starting to have all this junk on them, right? These prefixes, and they're not easily describable as fixed points of morphisms in some cases. So maybe it's the morphisms that are really the more natural thing to be asking about, but I don't know what the right question is. So I don't know what question will give these two morphisms as answers. The morphism for 3/2 preserves 3/2 powers. The morphism for 5/4 preserves not 5/4 power freeness, but pre-5/4 power freeness, as long as you avoid some letters. Right, but that can't be the whole story. I don't know how to ask about morphisms that generate Lex-Least words without actually generating the Lex-Least word. So if anybody has thoughts on that, I'd be interested to know. But I will stop there. Thanks very much.
Thanks a lot, Eric. Does anyone have any questions for Eric? Maybe I'll just ask, is there any sort of intuitive reason for why these words should take so long before their self-similarity should sort of kick in? Is there any way to understand why it takes so long?
I don't think so. Yeah, I think that's one of the mysteries. Yeah, and some of the words that we don't know the structure of, maybe they, they take even longer, or maybe they just don't. Yeah, I think we don't know. So I mean, what I think the temptation is when you're running into these really complicated things, the temptation is to think that you're asking the wrong question. So, and that goes back to my previous slide here. It's like, maybe this is the wrong question, but I don't know what the right question is. So for now, the only approach that I have is to continue to look at these Lexis words, and hopefully the the grand theory will become clear at some point. But yeah, I just don't know.
So are you like hoping maybe there's some kind of like number theoretic connection, like these are related to base 6 expansions of numbers in some interesting way, or?
Yeah, quite possibly. Yeah, I really don't know.